thanks a lot for organizing this. This must be a tremendous amount of work for you, Tavi. I'm really pleased that so many of you are showing up across the different time zones, and because I respect your time, I'll just jump right in. So this is something that I've been working on for a few years. The last few years, kind of getting interested in the physics of radar reflection, what controls it, and what might we be missing with the kind of most common but simplest approach that has been taken in radioglaciology in the last several decades. And just to make it kind of flashy and interesting, I'll focus the talk on subglacial lakes, both on Earth and Mars. I had the pleasure to collaborate with a group of planetary scientists recently. We published a GRL paper maybe a month ago on the application of kind of a more complete, as I believe, way of interpreting radar reflection to the lakes that have been proposed to exist beneath the South Pole layer deposits on Mars. And as always, I thank a lot of the colleagues who've suffered through working with me on different aspects of this that relate to the presentation, but they are not to be blamed for any mistakes or misstatements I'll make. It's all mine. And of course, NSF for continuing funding and U.S. Antarctic program for getting me to Antarctica from time to time to keep me motivated to work on these things. Oops. So let's just get started. Review for many of you. Subglacial lakes exist, as many of you have worked on, in Antarctica abundantly, and some in Greenland. So we have bodies of water of different sizes beneath the ice sheets, smaller bodies of waters beneath glaciers and ice caps. And it looks kind of like this. It's a nice figure from colleagues who've published a paper recently. And in many ways, subglacial lakes are of scientific interest and general interest. Many people from general public who talk to me get excited when they hear that there are lakes, some of them as large as some of the Great Lakes here in U.S., beneath the ice sheet in Antarctica. And suddenly on Mars, there's been a lot of talk about subglacial lakes since 2018, since the publication in Science that came out speculating that some of the bright radar reflections found in the Mars's data beneath the South Polar layer deposit may be subglacial bodies of brine, lakes, liquid water, which, obviously that's kind of a big target for NASA to be chasing because we think that that's our best bet at finding life on a planet that's different than this one, another version of a tree of life that is separate from the tree of life that we have on Earth. And then on Earth, of course, subglacial lakes have been also a vigorously investigated target. They're analog microbial habitats for ocean worlds, and also unique terrestrial habitats for microbes on this planet. They modify fast ice flow, and they help determine maybe when ice streams start. So how ice flow patterns within the ice sheets organize. And then they represent potential paleoenvironmental archives that we can tap and interpret the past conditions beneath the ice sheet from the sediments contained in subglacial lakes. So quite an interesting topic to be looking at. Well, for some reason, I'm having a hard time advancing. Here it is. It's probably a large figure. So what's the connection between subglacial lakes and radar? Well, this is the way that we or scientists have realized that there are lakes beneath the Antarctic ice sheet. This very nice figure is not from the earliest papers, which are listed, to the right, like Oswald and Robin, but from later paper by Tobacco, where they have collected radar lines over Lake Vostok and have shown very nicely, as you can see in the top panel, that the radar power reflection coefficient increases significantly as you fly from being above the interface between ice and bed to the interface between ice and water. Very strong reflection there. And then as you come off the lake, your bed reflection drops in strength. Very nice illustration of that. Of course, in the first several decades of work on subglacial lakes, in addition to radar reflection strength, there were other criteria that were, required or used to basically convince reviewers and others that what we're looking at are indeed large bodies of water beneath the ice sheet. And that those other lines of supportive evidence include, for instance, flat spot. Flat spots on the surface of the ice sheet, because where the ice layer floats over water, obviously there is no basal shear stress, and the ice basically spreads kind of like a confined ice shelf. So you have very low surface slopes. You have also characteristic patterns of both topography and ice flow as the ice enters large lakes and then exits from large lakes, with extension on one end and compression occurring on the other end. So the bed reflection strength wasn't the only one, but certainly became a very important factor in how we interpreted subglacial lakes. In more recent years, I've seen papers where, basically we switched to just the bed reflection strength being the criterion for detecting lakes, and maybe even automatically detecting lakes through some kind of algorithm. Through all these different efforts, we've benefited from consistent work of people like Martin Siegert, who's been cataloging and mapping out the lakes that exist beneath the ice sheet, and combining the large lakes that were detected through radar surveys with the active smaller lakes that were detected through deformation of the ice surface, like in the original paper by Helen Fricker and others. And we know that there is an extensive system of lakes beneath the Antarctic ice sheet. When we change planets and hop a little bit towards the outside of our solar system, there is a south polar layer deposit around the South Pole, and we've benefited as scientists from having two radar systems that have been imaging Mars overall, including the South Polar Layer deposits. And these two systems are MARSES and SHARAD. This one operates at somewhat lower frequencies, 3, 4, 5 megahertz center frequencies, and then SHARAD is either 20 or 30. Probably because of that higher frequency, SHARAD tends to reflect less from the bed. It doesn't produce a bed reflection as much as MARSES, and hence the mapping that exists of the basal radar power coming from the bed on Mars is mostly from the lower frequency MARSES radar. And this is there's been actually a sequence within the last few months of 3 papers published by GRL on this issue of subglacial lakes and bed reflectivity on Mars, including this paper by Kuller and Plaut, where they basically systematically, rather than focusing on any specific high reflectivity anomaly. They systematically have mapped out the bed reflectivity. This is shown here. This shown in terms of, the relative power coming from the bed relative to the reflection from the surface of the South Polar layered deposits. And that's expressed in dB color scale right there in the left corner. So you can see this kind of speckly nature from really very high reflection strengths to, strong but much weaker reflection strengths. And not necessarily coherent. Some of the strong reflections coming from right near the margin of the layered deposits where the ice thickness or the thickness of the deposit is relatively small. And that will become part of my discussion later on. Perhaps more a visual way of looking at these bed reflections is the lower right figure, which comes from basically fresh off the press paper by Smith et al., also in GRL. And it shows regions of strong bed reflection. So like the regions that were interpreted as subglacial lakes are these kind of localized strong bed reflections beneath relatively thick ice, or I'll keep calling it ice just so I don't have to say polar deposits every time. So we have these kind of localized, localized bed reflections, but also ones that are coming all the way up to the edge of the ice cap right there. And that is quite important. So let's zoom back to 2018 and to the paper that interpreted some of these kind of more interior anomalies, high reflectivity anomalies as subglacial lake by U.S.A. and colleagues. The figure on the left is a nice interpretation or nice illustration of the Marcis lines with the calculated basal power normalized to the ice surface power, as I said before. And so we have this localized anomaly that's crossed by several Marcis lines, surrounded by, quite distinctly lower bed reflectivity. And that kind of gave rise to the interpretation and the physical basis, the theoretical basis for the interpretation that we're looking potentially at the lake is shown on the right-hand side diagram, where we have probability distribution functions from that paper, from figure 4 in that paper, for the area where we have this high reflectivity anomaly contrasted with the area surrounding it. So that's the brown versus blue. And the x-axis shows you basal permittivity. So the calculated basal permittivity that explains the reflection and from their probabilistic model. And you're looking at permittivities that are dozens of units of relative permittivity. So dozens of times greater than the permittivity of empty space. So not necessarily, the peak doesn't occur necessarily where pure water is, which would be more like 70, 80 right there, but it is pretty high and definitely higher than the reflectivity of the regions outside of the anomalously bright reflector. Okay, so that's the U.S.A. paper. And just to dive a little bit more into the physics of how U.S.A. et al. And also most commonly in glaciology and planetary science, reflection from a ice over something interface is interpreted. Here we are. Yeah, this would be your typical real reflection, amplitude reflection coefficient, being given as a ratio of the difference between square roots of permittivity of the two materials, with epsilon 1 here being ice, and epsilon2 being the sub-ice material, and then divided by the sum of these, of square roots of these two permittivities. So permittivity of ice and permittivity of sub-ice material. So that's a nice, simple model for how radar reflectivity works. And this is definitely what basically led to interpretation of the little high reflectivity anomaly on Mars, or anomalies, because there's more than one, on Mars as subglacial lakes, because we know that water has a very high relative permittivity, depends on solute content and temperature a little bit, but let's say around 80 would be the most commonly quoted and used value. So that's 80 for water and about 3 for ice. So if you difference the two here, you're going to get a strong reflection, and this is what leads to interpretation that beneath the south polar layer deposits, we have bodies of water that are liquid and thick enough to produce reflection, which basically means that, deep enough to be comparable to the wavelength of the Mars's radar, which is like dozens of meters. Okay, so RSA's interpretation is basically following a long tradition in radioglaciology of using ice penetrating radar as a subglacial water detector. It's used for other things, of course. It's used to measure ice thickness, very fundamental and important quantity. But in terms of interpreting what's beneath ice, the only thing, because radar doesn't really penetrate into the sub-ice material most often, then we are really left with using the reflection strength as a kind of an indirect way of probing what's beneath an ice layer. And most often in glaciology, that very simple model that I just showed you, the one involving differences between permittivities, is used. And what it means is that we're basically using ice penetrating radar as a subglacial water detector. We're saying that the only thing that controls the strength of the reflection is the amount of water at the base, because that is what controls the permittivity of that bed. And you could say to some extent that is certainly justified because of that large difference in permittivity of liquid water, water in its liquid form versus permittivity of water in its solid form. A factor of 20 or more, that's a big difference. But, there is other things that may matter, like electrical conductivity of geologic materials, which also can vary or be different from electrical conductivity of ice by orders of magnitude, mostly being larger by orders of magnitude than electrical conductivity of ice, because ice is not a very good conductor compared to most geologic materials. Another, brief note, when we talk about the permittivity of liquid water, and especially in relevance to the discussion of permittivity of brines, because on Mars, the only way that you could have liquid, bubble of liquid beneath the ice cap there, due to the very low temperatures, it would have to be very, very saline. Yeah, we were talking about the very highly concentrated brines. The permittivity actually does vary according to at least these lab measurements by Meady and others, where they went from distilled water to roughly the conductivity of seawater, and found a pretty strong dependence of the measured permittivity as compared to the predictions from a theoretical model. So that's another thing to keep in mind, is that even the story of permittivity, even if we keep the story of what radar reflections from the bed means simple and just focus on permittivity, it is a little bit more complicated than just assuming that, oh, well, water is 80. And the way that it works for brines, especially, it's dropping with solute concentration. So we would expect that actually it is lower a briny lake like the one that has been hypothesized for Mars. So, the bottom line is that if we just throw away everything else but keep permittivity, then radar becomes a water detector, and it certainly has been used like that just to give you an example of a publication focused on detection of water beneath ice from radar lines flown in Greenland. And it's nice and simple, because then your reflection coefficient follows that equation that I just showed, and it's a one-to-one relationship. You can measure the reflection coefficient of something and then read off what the corresponding relative permittivity of the sub-ice material should be. And that is, the theory behind U.S.A. et al. Interpretation of radar reflection on Mars. Okay, but as much as I know, everybody hates to look at too much theory in a talk. I'll take you for a journey. I can't promise that it's going to be a short journey, but some journey to fundamentals. So here it is, one of the forms of Maxwell's equation, which is the equation governing propagation of electromagnetic waves. And that system of equations, which tells us everything about how EM waves behave, how they attenuate and reflect and so on. That system of equation contains three material properties. One of them is our familiar permittivity that we already know and love. The other one is magnetic permeability. And then the last one is electrical conductivity, which basically controls, among other things, attenuation in the material. So in theory, if I would be just a cold-hearted physicist looking at these equations, I could tell you that basically whenever you have an interface across which either one of these three material properties changes, you can get a reflection. You don't need to have it. You can have an interface across which the permittivity is the same, but one of the other quantities differ, and you will get a reflection of some amount of EM wave energy that depends on where the reflection energy is right there, and this is the incoming energy. And it depends on, just like with permittivity, on kind of the magnitude of the contrast in either the electrical conductivity or magnetic permeability. Oops, sorry. And basically, when somebody jumps right into using this equation and never talks about magnetic permeability and electrical conductivity and why they are justified to use this equation, to me, that's kind of a scientific, maybe not a sin, but certainly a faux pas. Because the two underlying assumptions of going from the Maxwell's equations to boiling down the reflection coefficient for a normally incident wave to this simple relationship basically means that you're saying that there is no contrast in magnetic permeability across the basal interface, which is, a decent assumption on Earth, because there is a relatively small subset of minerals and rocks that actually are magnetic enough to produce reflections. But still, there will be cases where there's going to be magnetic materials beneath ice. We know that there are magnetic metal ores on Earth. But the other, probably much bigger jump that one makes by choosing to use this simple version of the reflection coefficient is that basically saying that there is no contrast in electrical conductivity between glacier ice and whatever is beneath the bed. And that is a big jump, because glacier ice is very, very resistant. So it has a very, very small electrical conductivity, whereas many materials on Earth, including sediments, especially sediments that contain clay, or sediments that are saturated with brackish or seawater or briny water, or even bedrock with low porosity that will be saturated with briny water or seawater, are tremendously conductive. And then finally, there are also, just like there are magnetic minerals, there are also electrically conductive minerals. As we know, semiconductors, we know that the metallic ores exist in rocks, or metallic minerals exist in rocks, can be dispersed at high enough concentrations, actually even in dry conditions when the electrical conductivity is not due to the conductivity of the solute inside the rock or sediment, can be high enough to worry about it. And if you want to have, a really gruesome walk through this topic, you can go into the paper we've published in late 2020. This is a table 1 listing kind of values of electrical conductivity from literature and permittivity, and then going through the question of what it means for reflection coefficient at different frequencies, because once, when you use this equation for reflection coefficient, then conveniently, there is no frequency dependence of the reflection strength. But as soon as you keep either magnetic permeability or electrical conductivity, then you will have dependence of the reflection coefficient and frequency. Okay, so I'm gonna spend some time scratching my head. Somehow, I don't know how, over decades, it became okay in glaciology and planetary science to just jump straight into the permittivity only formulation for a reflection coefficient. And I just want to make a little appeal here that as authors or co-authors, we have the responsibility, and it happens for other theories, like we use other theories, how ice deforms, plenty of other theories that we use in glaciology where we have to justify our simplifying assumptions. And somehow, in case of the permittivity only formulation for radar reflection, mostly it just is taken as gospel without justifying the assumptions. So I implore you that as reviewers and editors, we have the responsibility to ask authors of manuscripts to follow rule number 1, which is fine, use that simplified equation if you feel it's justified, but please do discuss what are the assumptions underlying this equation, and discuss what the potential impact of these assumptions on your results is. And then the other scratching that I've been doing once I kind of, dug into this topic and realized how this is playing out in the field, why did it become such an automatic thing to use the permittivity only formulation? I mean, I have to give credit to a number of people. Yeah, there is a subset of literature concerned with radar use in glaciology and planetary science that has been taking into account electrical conductivity. Well, the permeability, the magnetic permeability is pretty much thrown out of the window by everybody. So I'm going to do the same too. But people have, used equations that include both permittivity and electrical conductivity. So why this has remained kind of a niche approach in glaciology? Well, one kind of a practical issue is that once you retain electrical conductivity, your reflection coefficient is not going to become easily real. It's a complex number containing imaginary terms, as shown here. On the left-hand side, you have the square root of -1 right there, multiplying different parts of the propagation constant for EM waves. So yes, in terms of the reflection coefficient at this point is still a kind of a complex number. It's not a real number. And even, these alphas and betas, if you start plugging in, they're kind of cumbersome. Yeah, certainly not the beauty and simplicity of square root of epsilon1 and square root of epsilon2 being the only thing that you have to worry about. And as I said, you're also retaining the frequency dependence of the reflection coefficient. Okay, last kind of thing that came to my mind, why is it that we've been kind of sticking to the permittivity only formulation for reflectivity is because the complex versions of that equation, for the most part, have used something that we are not using in geology or geophysics much, or in earth sciences, which is the tangent of loss angle, which is a great quantity if you are measuring the dielectric properties of a material in a lab. And this is what physics or engineering people will do, take a little sample of the material you're working on and measure both the real permittivity and then the tangent of the loss angle, which is related to electrical conductivity. Well, the problem is that doesn't speak so readily to geophysicists or geoscientists in general, because we don't really think or measure geo quantities in terms of a tangent of loss angle. What we do use, however, for over a century is the concept of electrical conductivity, or the reciprocal of that concept, which is the electrical resistivity. So plenty of geophysical techniques out there and studies out there that are measuring the resistivity or conductivity of geologic materials, but not in terms of the tangent of loss angle, but in terms of more to us tangible quantities, like these quantities that are expressed in, say, ohm meters or Siemens per meter. So I think that might have been also a barrier into kind of accepting or incorporating treatment of electrical conductivity in bed reflection. Okay, so how to keep it real? And this is basically, it's not a nice, colorful, satellite-derived map of anything, but it is kind of the meat of the paper that we published. And basically, when you take an absolute value of the complex reflection coefficient, then you can get the real component of it, which is now, still cumbersome. Yeah, those alphas and betas are still there, and they're expressed in these ways. But everything now in here is real. There is no square roots of -1 anywhere. And you can start plugging in real values of permittivity, of conductivity, of magnetic permeability, if you choose to, and a frequency of your radar signal. And yes, cumbersome, but you can basically do this in a spreadsheet or with a simple Python code or MATLAB code, and have a full accounting for how these different material properties can impact radar reflectivity of an interface. Okay, so just to illustrate how this kind of a treatment differs from the permittivity only treatment, here's a plot of these families of lines that represent the reflection coefficient for different assumed electrical conductivities on the x-axis and different assumed subglacial permittivities, because ice permittivity is pretty much fixed, 3 point something. So here it is, in this regime on the left-hand side, we're operating basically in the permittivity only. This is where it is justified to use the permittivity only formulation. There is no, all the lines are more or less horizontal, which means that there is no dependence of reflection coefficient on electrical conductivity. And then, this is for a given frequency of 100 megahertz. Then this starts to roll over and you start developing, pretty sensitive dependence of the reflection coefficient on conductivity. And then ultimately in the kind of right-hand side regime, we collapse all these lines together. So it no longer matters what permittivity the subice material is. The permittivity of subice material is negligible, or its impact on reflection coefficient is negligible compared to the impact of conductivity on reflection coefficient. And that's, given, basically this is the electrical conductivity version of this equation, where only electrical conductivity of subice material matters to reflection strength. So you have these two end members, in physics, this one would be called high loss, and this one would be called low loss. And then in between, in this transition zone, you have this messy transition zone where, kind of both matter, and you should be really using this equation to capture the dependence of the reflection strength on both the permittivity and electrical conductivity. Oops. All right. I'll point out one more problem and an opportunity with the transitional regime, which is it's a regime in which you have reflection strength and then two things that determine it, which is the sub-ice conductivity and sub-ice permittivity. So it's a one equation, potentially it's a one equation with two unknowns. So you need to bring in other constraints. One approach could be you measure the phase shift angle of the phase shift of the reflected wave compared to the incident wave. And that way you get a new equation. So then you would know if you measure the left-hand side and you have a second equation dependent on the same thing as the reflection strength, and you can solve two equations for two unknowns. Or you can use this approach, which would be using multiple, at least two or more radar frequencies, measure reflection strength at different radar frequencies. If they don't differ between frequencies, that means that electrical conductivity doesn't matter, and permittivity is what dominates the reflection strength, because permittivity is the part of the reflection strength that is determined by permittivity is frequency independent. And then if you do see differences between frequencies, then you can calculate basically explicitly calculate from at least two values of reflection strength for a given place at two different frequencies. You can calculate the permittivity and the electrical conductivity of the sub-ice material. And these are just kind of illustrating. This one is the shift, the tangent of the phase shift angle as a function of electrical conductivity for 100 megahertz, and then amplitude of reflection coefficient, how it changes for different conductivities, and so on. So, okay, by now you're exhausted of all the theory. We're going back to Mars and applying that theory. So hopefully that's a little bit more tangible for you. It's still pretty abstract, so hang on. This is that GRL paper led by Carver Beerson, who used to be a graduate student here and is now at Arizona State University, and then with Sam Carville and Tan Putzig as co-authors. Carver took my equations for the kind of conductivity dependent reflection strength and Sam Carville's existing model for radar wave propagation on Mars, and combined these. And what did we find? Well, what we found is basically boiled down in these plots down here. So we have the observables, which are these dashed lines here. Those are the observed reflection strengths from the three Mars's frequencies, 3, 4, and 5 megahertz. And it's kind of nice that those are pretty low frequencies, because the lower the frequency of radar, the more likely it is that it is dependent on electrical conductivity. Basically, it depends on lower contrasts of electrical conductivity than higher frequencies. So in this case, electrical conductivity should matter a lot, because we're close to 1 megahertz. So here is, our theoretical lines of reflection strength as a function of conductivity of the sub-ice material, and then they intersect the observed lines here in this region. So basically, within a zone where we have conductivity of between 10 to the minus 3 and 10 to the, around 10 to the minus 3 for Mars's, which is pretty, not that conductive. It's in terms of resistivity, we're talking something that's like close to 1,000 ohm meters. 1,000 ohm meters on Earth, that would be resistivity of like bedrock. And then we also have a line for Charade radar, which unfortunately you don't see a fourth dashed line. That's because it didn't produce a reflection for this area, and this is the area where U.S.A. et al. Have hypothesized the subglacial lake. So basically, we can explain the reflection strength with just conductivity in the area of the proposed subglacial lake. The other important observation is that reflection strength as observed by the Mars's radar seems to be frequency dependent in the way that's consistent with that equation that I showed you before. Okay, so whereas our results do not explicitly completely exclude the possibility of sub-ice liquid water, because liquid water can also be conductive, but are consistent with other electrically conductive materials like saline ice, wet clays, or just conductive metal-bearing minerals that can be completely dry, don't require any water. One of these minerals that has high conductivity is jarosite, and that would basically require zero water beneath the ice, being present beneath the ice for that high reflection to be present. The other problem with retaining lake water, briny lake, as an explanation is that, well, if it's a briny lake, it should be electrically much more conductive than 10 to the minus 3, basically. Hyperconcentrate, like seawater, is already, at least on Earth, and temperatures on Earth, is already like 3 to 5 Siemens per meter. And we would expect brine to be somewhat higher conductivity. So I think that that it is very unlikely that our explanation, our results of our paper, are consistent still with a briny lake. And then there's the general problem that maintaining liquid brine at depth of 1.5 kilometers on Mars requires heat fluxes that are several times greater than the typically estimated heat flow on Mars. So, here is a plot that basically is from Sori and Bramson 2019 paper, where they basically say that you need like 90 milliwatts per meter squared, which even on Earth, that's a decent heat flow. But on Mars, you're talking basically about estimates of background flow being closer to these blue and green lines, which would not allow even very concentrated brines to be liquid. The other problem that popped out from one of the recent papers is that you have so much high reflectivity beneath the South Polar layer deposits, including very close to the margin, including under very thin ice. So this is a scatter plot of these reflectivities showing that you can have high reflectivities beneath ice that's like less than a kilometer thick, which would only increase the problem with how, if you want to explain these high reflectivities with water present beneath the ice on Mars, how do you keep that thing from freezing when the ambient temperatures are like 160 or 170 Kelvin? And then this is just going back to that illustration of the fact that some of these clear conductive, reflective horizons beneath ice go all the way straight to the margin. And Smith et al. Pointed out the problem with interpreting these types of high reflection interfaces as ice over water interface. And yeah, they actually proposed, have done some lab experiments and proposed that a smectite that has been frozen to temperatures not as cold as 170, but pretty cold in a lab is retaining enough liquid to be conductive enough and to have high enough permittivity to explain these high reflections on Mars without a lake. Okay, subglacial lakes on Mars. To me, it starts to look more like Bitcoin rather than solid gold in terms of what's backing that interpretation. As disappointing as it is, I love subglacial lakes, and I would love that there would be subglacial lakes on Mars, but as a scientist, I'm not supposed to be guided by emotions, but by evidence. Okay, so we'll take a quick trip back to Earth. And this is an image that's been graciously given to me by Matt Siegfried and Dusty Schroeder from their work on bed reflectivity over lakes in the Sipal Coast region. This is outline of the subglacial lake Engelhard, or Engelhard subglacial lake, whichever way you prefer to say that. And you can clearly see the reflectivities are, expressed with this color scale down below. The browns are strong reflectivities, the blues are low reflectivities, and it's actually the reflectivities are higher outside of the lake than they are over the lake. And, if you would use the, permittivity only formulation for bed reflectivity, it would make no sense. But if you incorporate the fact that till, which is what surrounds the lake here, is clay rich, we know that from samples that were brought up to the surface decades ago. It's like 30 to 40% clay, it has 40% water, and it's highly electrically conductive. And this is why that till can give you a stronger radar reflection than pure water, than 100% water, which would be impossible under the permittivity only formulation. Under the permittivity only formulation, when you have pure water, you hit about 67% amplitude reflectivity, and you can't get any higher. When you incorporate high conductivity of clay-rich sediments, then you can get to almost 100% reflectivity, and you can basically have the situation where the reflection from till that's conductive, is significantly higher in strength than reflection from just 100% water lake in Subglacial Lake Engelhard. Okay, and just to bring this to a close, I'll run through some of the take-home messages I want to leave you with. So, radar interpretations of bed reflections on Earth and Mars focus too much on high permittivity of water and ignore the possibility of electrically conductive subice materials. And then we have offered in the paper published in the Cryosphere in 2020 an attractable approach where you don't have to deal with imaginary numbers, but you can use it to incorporate electrical conductivity interpretations of bed reflectivity, in addition to treating the permittivity of subice materials. There's no need for complex variables, no need for abstract and rarely measured by geoscientists quantities like tangents of loss angle. Yeah, the case for liquid subglacial lakes on Mars, I think, has been weakened by the several papers that have been just published in GRL. And an alternative explanation is that we're basically looking at electrically conductive materials, some of which may have zero water whatsoever, like jarosite, as a thermodynamically more plausible explanation. And then going back to Earth, we may be overinterpreting bright reflectors as subglacial lakes in Antarctica and Greenland. Wet glacial sediments can produce very similar radar signatures, especially when you're dealing with relative rather than absolute bed reflection strength. And I believe very much in the number 5, which is that, yes, it is going to be kind of a little bit more work to worry about two quantities, permittivity and electrical conductivity. But then we will be wrong less often if we do that. And then also we open up new avenues for using radar to map out new things. Yeah, now radar becomes something more than just a water detector. It becomes a detector of water and maybe clay-rich materials like clay-rich sediments and rocks. Other planetary bodies like Europa, you can maybe fly a multi-frequency radar and use that data to actually get constraints on what is the salinity of the ocean beneath the ice shell on Europa. And that would be it for me, but I want to advertise or let Tavi advertise the talks that are coming up.
Yes, thank you very much indeed, Slawek. And just to encourage everyone to come to next week's talks, we continue some radar, and we have also talks about both Greenland and Antarctica. But let's go for questions for Slawek. If anyone has a question, if you'd like to pop them into the chat. I think, Roger, you probably are first there if you want to unmute yourself and make your question or comment, I think it might be.
Yeah, yes. So thanks very much indeed. Really enjoyed that. And as my comment in the chat says, there's fantastic parallels here with seismic where most people don't take any notice of the attenuation contribution to reflectivity, which changes the phase as well as the magnitude of the reflection and transmission coefficients. So I fully agree with your conclusion 5 that there should be a paradigm shift in how GPR reflectivity is managed. I was just wondering whether or not there are any lab experiments, excuse me, or field experiments that have actually given you some control on this. Certainly, there have been in seismic where people have done laboratory experiments at ultrasonic frequencies with various materials underneath, in tanks of water that have proven the theory of the attenuation contribution. And just wondering if you've got any ground truth examples.
Yeah, great question. So the only kind of ground truth or testing whether this works that we have done, or I was involved in, is that work on Marsis and Charade reflectivity. Unfortunately, Charade, which is like 10 times greater, higher frequency than Marsis frequencies, did not give us the reflection coefficient at the locations where the subglacial lakes have been hypothesized. So that would have been a better test. The only test we have now is that within that range of a few megahertz, it seems to work that the reflection strength decays as the frequency is increasing, which is consistent with what happens when your reflection strength is dominated by electrical conductivity.
Smashing. I was just thinking, my house sits on 77 meters of quaternary glacial till. So if the basement ever floods, we'll come and do a GPR experiment in the basement and see what we get. Thanks very much indeed.
Thank you.
Trevor, do you want to unmute yourself and ask a question?
Oh, well, thanks. Yes, I mean, I guess to have liquid water on Mars, the temperature would really have to be very high. But my question is, are there any areas where there is a coincidence between the flat ice surface and a reflector below? If there are, then it does tend to go against the argument, but I presume there aren't.
So I'm trying to understand. You're asking if there are places where you have kind of flat surface. The flat surface is a great, additional line of evidence if somebody's mapping out subglacial lakes. And I must say that, I think it was in the beginning of mapping out of subglacial lakes, we were kind of more rigorous. So, kind of let's call it the Seagard age of mapping out of subglacial lakes. They would really kind of go after multiple lines of evidence to call something a subglacial lake. Over time, as the subglacial lakes have multiplied, we've become a little bit more relaxed about what it takes to call something subglacial lake. I do want to say that, potentially wet clay-rich sediments can be very weak, yes? Like we know that the clay-rich tills beneath Whillans and Kamba ice stream, they're basically few kilopascal shear strength. So I think in terms of kind of the ice slope argument, you can have pretty flat slope over wet sediments as well as over lakes. So that makes it difficult to kind of, really pin down. Unfortunately, it seems to be like the golden standard is the seismic, but it's so much work and you cannot put it on a helicopter or a plane.
Thank you.
Do you want to unmute yourself and ask a question? You have your hand up. Ramesh Singh?
Yes. Okay, then it was a nice talk. I really enjoyed. I would like to know, like you have published a paper in a GRL. What was the frequency of the radar for the Mars mapping? And if it is a L-band, in your talk, you covered about the conduction currents, where you talked about the the permittivity and the dielectric constant. But in remote sensing, in the microwave, it is better to define the imaginary part of the dielectric constant, which is of course related with the conductivity. But I want to see that one thing, but you did only cover up to 100 megahertz or 800 megahertz. But if you go above that, then it is good to define the complex dielectric constant. Thank you.
Yes, so I agree with you. I'm trying to, get away from the complex, reflection coefficient and dielectric constant, because I think that it represents a barrier to, adoption of a kind of more realistic model for radar reflection as it is used in glaciology and even GPR studies. But you're completely right. There's a whole world out there that uses the dielectric constant as basically a combination of the real permittivity and the electrical conductivity. This is kind of the world that I'm trying to stay away from. So the equations that we have in this paper are based fully on kind of the very old textbook, Stratton, 1941, and in which he derives these reflection coefficients and states explicitly that in this case, his solutions work only and only if the material properties are real quantities. So, I can't tell you if somebody afterwards proven that his solutions work if you're using, a permittivity that has both real and imaginary component. But certainly in Stratton's book, right after derivation of these equations, he says that the alphas and betas, they're real quantities that are dependent on real material properties. They cannot be imaginary quantities for his solution to work.
No, I agree there, but if you take a microwave remote sensor book by Ulabi et al., you talk about the real part and imaginary part, and Stephen is here. Stephen, he has carried out both the measurements, and I have also carried out both the measurements. But there is a confusion these days because I just published a paper in Remote Sensing, International Journal of Remote Sensing Letter, where, of course, a real and imagery part control the response of the active and passive remote sensing. And when I talk about the backscattering, with the contaminant in the water, and the people get confused, and I believe we do not have a much understanding of that. Anyway, thank you very much.
Thank you.
Steve Warren, do you want to unmute?
I really enjoyed your talk. But I had a related question to the previous one about this transition region where intermediate conductivity, where in the frequencies that are used in glaciology, the permittivity of water is pretty much constant, and so is ice, and they both have very low absorption or very low conductivity. But possibly these geologic materials that might be below the ice would have conductivity varying with frequency. So it seemed like for your solving two equations, two unknowns, you required the conductivity to be independent of frequency.
Yeah, that's a very good point. This is where we are entering a very dangerous world. I mean, let me find, let's see here. I mean, permittivity is usually taken to be, in glaciological interpretations, in a very narrow range, but even this plot shows that reasonable solute concentration increases can change the permittivity. So I think there's a lot of complexity and this is one of these studies where, they've taken water of different solute concentrations to a lab and have done the real and imaginary part, with the imaginary part being conductivity dependent. And one would have to go to studies like that to really determine whether the range of frequencies that you're working with represents the range of frequencies in which the conductivity is constant, which is basically the imaginary part then falls off as a straight line because it involves division by frequency. It falls off with frequency as a straight line. So I believe for the paper that we published, we were, as much as possible, when people gave us the frequency dependence, we were checking and trying to adjust for any frequency dependent. But I agree with you that there is that world in which we are looking at, potentially different. What electrical conductivity is not necessarily the same as it is measured by DC methods or even low frequency inductive methods. It is a world in which we would have to start worrying about those issues. But there is a literature, like, I've discovered this paper by Meade et al., really comprehensive study of permittivity, real and imaginary parts of permittivity of water. So I think there is already material that we can tap into, and then other people can maybe make measurements at the ranges of frequencies and materials that haven't been yet studied as much, like, for instance, clay-rich sediments. Yeah.
Neil Ross, are you able to unmute yourself and ask your question?
Yes, thank you very much, Slawek, for a really interesting and accessible talk. I was interested in the kind of application of some of the things you talked about with the multi-frequency and things like that. And I wondered whether there was application to kind of, maybe test hypotheses of where there might have been grounding line advances over ocean water and training the material, the water, salty water in the sediment.
I think that is probably one of the juiciest right now at the moment potential targets of seeing whether whether grounding lines have been mobile, going back and forth, say during Holocene, because when they re-advance over marine sediments, you might have quite conductive material beneath ice. So that certainly is something that I hope somebody will look into with existing data, maybe collect new multi-frequency data, because I think that has a lot of potential to really elucidate this question of whether, how stable, how much smaller or how much retreated the grounding lines might have been in the recent past.
And Kirk Scanlon.
Yeah, my question is more just carrying this a little bit further. Like, all the equations we saw were all for an interface between a flat interface between two homogeneous half spaces. Like, how this gets even more complicated when you start throwing in, like, sub-resolution layers or surface roughness. At what point do we have to say, like, we have to just pick on the simplest solution and move forward, as opposed to considering every possible pathway that could modify a reflection coefficient or an observed power?
Great question and point. I'm lazy, so I only dealt with equations for for normal incidence. But actually, the same 1941 textbook has a solution with the alphas and betas, which is kind of cumbersome, because it involves a lot of geometric factors that includes both the angle of incidence of the wave, and also it includes a finite thickness of a layer. So those solutions exist that again keep the problem in the real realm. And I think even McGregor and Christensen, the papers that they've published that did take into account through a complex treatment of radar reflectivity, they did take into account the finite thickness of the sub-ice layer. So it's doable. It's just a little bit more, cumbersome, but it's not again, it's just a matter of writing a little bit longer code, or it's not intractable.
Thank you. Dale Weinbrenner, I think you've got a comment rather than a question there, but you want to unmute yourself and make that comment? Is Dale there? His comment is on the chat, and he comments that there might be a difference between Mars and Earth, and that we might not get the surface flatness on Mars because we might not get very low basal traction, and there might not be enough mechanical strength in the ice to sustain topography. I don't know if you've got any comments on that one, Slawek.
Yeah, I mean, so the nothing that I talked, again, the limitation of what I talked about is this is a flat interface. There's no scattering, no complications like that included in here, but it is consistent with what has been done in the field, which is, you know, kind of partitioning, writing a radar equation in which all these things are represented by a different term. Yeah, so I didn't feel like we have to do everything in one paper, but yeah. As far as I understand, you know, anything that happens to the interface, say on Mars, would tend to make the reflection weaker, like say scattering. There's probably a way of making this an upper bound or one-sided interpretation, or one-sided bound on an interpretation of what's beneath ice on Mars. Rather than, you know, an exact. And then, you know, somebody hopefully who has more time than me and is smarter than me will come around and do a full modeling that includes all these complications. I think Sam Corville's treatment of radar propagation on Mars that we used in the Carver-Beerson et al. Paper, that includes scattering at the surface. Like you have knobs there that you can turn to take that into account.
Thank you. And I think the last question probably is from Anya Rittershauser.
Oh, yes, here. Yeah, thank you so much for this talk, Slawek. That was great. So I was wondering, maybe that's more geology question. Do you know if clays, when they become frozen, can they retain a high conductivity? Like at the example on Mars, that there's a type of clay that has high conductivity even when it's dry. Is there something that could exist on Earth like that?
That's a great question, and I would direct you straight to the Smith et al. 2021 paper that just came out in GRL, where they treat exactly that. That's their favorite explanation for Mars. They basically said, okay, if we take saturated smectite clay and then cool it down to, I forgot, 206 Kelvin or something like that, is it still conductive? So they did actually run these, you know, real and imaginary part of dielectric constant lab experiments on frozen clay, showing that there is still you know, significant retention of water. They chose smectite because it's a, you know, water. It's a clay that very freezes. As it freezes, it still retains some liquid water layers along the boundaries. It has a huge surface area, so it is the material that will retain liquid water to very, very low temperatures, and especially if that water would also be, you know, rich in solutes and so on. So I think on Earth, going back to Earth, when I was younger and I thought about permafrost and freezing tills and things like that, there's suddenly a good literature in the engineering world where they took clays and froze them, and they can show that there is still unfrozen water content left at minus 10 degrees C or minus 20 degrees C in some of the clay-rich materials.
Okay, I'll have to dig into that literature. Thank you.
Sure.
I think we've run out of questions there. So an enormous thanks to the audience for providing so many thought-provoking questions, and a huge thank you to Slawek for keeping us all riveted by Maxwell's equations, which is quite impressive at what must be after 11 o'clock in parts of Europe. So thank you so much. Really clear, elegant presentation and really thought-provoking. So thank you very much indeed. And thank you to everyone. And next week is the last of the summer series. Then we'll have a holiday before the autumn. But thank you again to Slawek.
Thanks a lot for organizing this.
Enjoy the rest of your day or good night, depending on your time zone. So thank you very much, everyone.